So the first thing we're going to talk about with the tsunami portions of the building code has to do with, let's say, more of the administrative portions of the code and some of the terminology that we're going to need to talk about using some of our other topics. So let's go to my slideshow. So I want to talk about the load factors and the importance values assigned with the tsunami portion of the building code. So, when the code writers get together and they think about how we're going to actually incorporate this into our projects, there are some questions that they're trying to answer. And for example, you know, here's a project somebody's working on. Does that need to consider all this aspects of tsunami loading or not? So does the structure I'm designing lie in a region where flooding is likely to occur? I mean, if I'm outside of a inundation zone, I can completely forget about this portion of the building code. But we expect that if flooding does occur, most structures are going to be very severely damaged by that water. The water damage alone is likely going to require replacement of all the architectural feature materials, building contents. The water damage will likely require replacement of several of the structural elements, but certainly the building code's intent is the structure should not collapse in the event of a tsunami, because that's when life safety really becomes a major risk. So there's a few different things the building code looks at to determine whether this is likely to be an issue or not. First question is, does the building lie in a location that's likely to be flooded? Secondly, does the use of the building make it more of a higher risk for casualties? And how should an engineer combine whatever effects this tsunami wave develops with other types of loads, dead loads, live loads, that also have to be supported by the building frame? So we're going to talk about three different aspects of the tsunami load provisions. First off is this idea of inundation depth and run up. Then we're going to talk about what the building code designates as a tsunami risk factor. And then for the third question, we're going to look at the load combinations. So the first way we're going to look at where is likely to have a tsunami wave is we're going to go to the USGS, United States Geological Society. They actually have what they call the ASCE Tsunami Design Geodatabase, which is literally maps of a large amount of the U.S. Coastline. And here's the map for Alaska, and actually shows all these shorelines of Alaska where they have data about potential tsunamis. If I think about what's happening during a tsunami wave, here is the ground surface. Here is the mean sea level, which is referred to as NAVD 88. This is the shoreline when there is no tsunami. Here's my building that I may be planning to build. Now a tsunami is generated. The water comes in. That water begins to wash into the land. Eventually, it reaches its combined total inundation distance. Is how far would that wave actually travel before it stops? And the elevation that it stops is known as the run up. If the structure lies within this inundation distance and parts of the structure are below the run-up elevation, we have to expect that the tsunami wave will impact it. Now, if I look at that USGS database in a little more detail, this is a map of the Santa Cruz region in Northern California. All these little triangles are data points that the USGS has data to provide. So here's a large picture of Santa Cruz. Let's blow that up so that we're beginning to look at just the downtown. And I'm even going to blow up that region of the downtown even larger, zoom in, and I can begin to see individual triangles. Here's the San Lorenzo River, which runs down on the edge of downtown Santa Cruz. All this blue shaded area, much of the downtown region, is expected to be inundated in a major tsunami. If I click on any of these triangles, then it actually tells me what is the run-up elevation based on the NAVD 88 for that location. So this edge of this blue line is the inundation distance and the elevation where I expect flooding to occur. So here's my inundation distance. Here's my run-up elevation. But the reality is that the tsunami wave is a dynamic event. There's a certain water level, but the energy that that water is carrying produces what's known as this energy grade line. The faster the water moves, the more energy it contains. It's got the potential energy of the weight of the water. It's got the kinetic energy due to the velocity of the water. That velocity stops when it finally reaches its inundation distance. So this energy grade line will be equal to the run-up elevation when I get to that inundation distance. To plot this energy grade line, the building code provides us several formulas. It's kind of a complicated calculation. There is an example available. It works on an iterative process. You start by calculating right here at the very end of the inundation and work your way back. But through that, you can plot this grade line to come up with the energy at any location. So my second question had to do with, so the first question is my buildings located in that inundation distance? Second question is, well, what's this building being used for? And so the building code uses what they call the tsunami risk category, which is based on what type of activities are going on inside the building. And it groups buildings into 4 different categories, 1, 2, 3, or 4. The higher the category, the more critical this structure is to society, meaning that damage to this project is at a higher risk to overall society than damage to some other structure. A structure with multiple uses, whichever use produces the largest risk will be used for the entire structure. These risk categories are similar to just the regular wind risk and seismic risk categories with a few unique features. So risk category 4, this is the highest risk type of facility. These are what are known as essential facilities. And in general, it's facilities that If we lose the use of this, it's going to create a very large impact on the ability to respond to the tsunami. So hospitals, police stations, fire stations, emergency communications, the types of first responder buildings that we need active immediately after a tsunami, these are the highest risk. If they're high risk hazardous materials, something escapes from this building, it's going to produce a large risk to a large amount of people outside of the building. Now, there are a few unique things for this tsunami risk category. There's what's known as a tsunami vertical evacuation refuge structure. So this would be a building that's being designated as a place where people should actually go to the upper floors of this building in the event of a tsunami, no matter what the building is really intended to be used for. This has to be risk category 4, because this is literally where we're directing people to go if a tsunami would occur. There are a few essential facilities that are not on this category 4 for tsunami risk. These are typically structures such as a building that holds, or a garage for ambulance or emergency equipment. The idea is that one difference with tsunamis versus the earthquake in general is the tsunami, I have a little bit of time to know that this event's going to occur. So if I have a garage that holds the ambulances that a community uses, I can manage my facilities with the idea that during a tsunami, the first thing we're going to do is get all the ambulances out of this garage. And then the garage isn't that critical for me to have functioning when the tsunami actually occurs. The city government does have the ability to designate what would be essentially facilities into a lower risk category. This would be based on redundancy. So in other words, if there are several fire stations in an area, perhaps the city can justify that they don't have to have everything at the highest risk category, because there are other facilities that can step in to provide them support. So risk category 3, these are what the code refers to as critical facilities. The importance factor here is going to be 1.25. So our forces are going to be increased by 25%. These are types of facilities that may not be required to be operational after an event, but damage to these could be much more severe to a larger population of people. So for example, theaters and auditoriums, someplace where there's a large assembly of people, any type of issue is probably going to create several casualties. Schools and prisons. Schools are housing a lot of young students, young children. They don't really know how to respond to events like this. And of course, it's a tragedy when something like that is badly damaged. Prisons, prisoners are not there by choice. They expect and deserve to be safe while they're there. The building code says we have to design those facilities to be a little more reliable in an earthquake, in a tsunami. Utilities, hazardous materials. Once again, building gets damaged, a lot of hazardous material gets out into the environment, can have a much wider impact than the loss of a traditional building. These aren't, like I say, they aren't required to respond to the tsunami, but they're going to create a large effect. Here I have a picture. The odd thing about tsunamis, this was a tsunami that hit Japan due to an earthquake in Chile. These tsunami waves can travel all the way across the ocean, and surprise people, even though they may have not even been aware an earthquake occurred. Now we get to tsunami risk category 2. These are basically just your traditional structures. Not that they aren't important, but they are the normal that the building code is addressing. They have an importance factor of 1. In other words, the formulas that the building code uses don't need to be increased or amplified because of some critical feature of the building. Commercial real estate, residential real estate, uh, almost all buildings fall into this risk category 2, unless they have one of those unique features we've talked about. Then tsunami risk category 1 is essentially what's known as unoccupied facilities. These are structures that really don't have human occupants, at least not on a rather permanent basis. Think of agricultural barns, storage facilities, places where people are maybe in and out, but don't spend significant amounts of time. So the building code goes through and then designates, you've looked at your building, you've looked at what is going on inside the building. If you're in that top risk category, no matter what, your structure has to be designed for these tsunami loads. If you're in risk category 3, which is not the most highest risk, but still they're critical facilities and they do pose a risk, then if my building has a ground floor that's going to have an inundation of more than 3 feet, I need to worry about tsunami loading. Now, obviously, 3 feet of water is going to do a lot of damage to the water damage to the structure, but that's not really what the building code is focused on. 3 feet of water probably is not going to do structural damage to the building. For tsunami risk category 2, a unique feature about the code, the city or the state actually has to have a specific ordinance or a statute that says that the buildings need to be designed for it. So the code does not automatically require the tsunami loading for all normal buildings unless the local municipality has explicitly passed an ordinance saying that it needs to be considered. In addition, for tsunami risk category 2, all 1-story buildings that don't have a mezzanine, don't have critical equipment, don't have an occupied roof are automatically exempted from the tsunami loading. Doesn't mean they won't be damaged, they won't be flooded, but they shouldn't be in a point of potential collapse if a tsunami wave comes in. So today, I'm not talking about how we come up with the specific loads on the structure, but we will be talking about those things. Once we do determine them, we're going to find out that there's generally 2 types of loads that a tsunami may induce. The code gives us symbol FSU for a load, which might be a force or a moment on some structural element due to the lateral force produced by this water coming in or going out after a tsunami wave. It's important to remember that we have to consider both the incoming and the receding wave. In fact, a lot of times the worst damage occurs when the water is flowing back out to the ocean, because then it actually has gravity assisting it and actually carries more energy than it did when it was coming in. There's another type of force, which is designated HSU, which is once again a force or a moment that's caused by the hydraulic effect. So literally the building or the structure may become buoyant and may actually be picked up somewhat due to the water surrounding it. So the building code says we're going to combine those with our other loads. One possibility is we're going to look at 90% of the dead load, the lateral force of the tsunami, the hydraulic force of the tsunami, or we're going to take 120% of the dead load, half of the live load, 20% of the snow load, plus the tsunami forces. These are written all in pluses, but we have to consider that these forces may or may not be combining algebraically. In fact, the code says anytime H tsunami actually is reducing the total, we should reduce it and only use 90%. So anytime the load on our structure is actually being reduced by the tsunami wave, then we should only consider 90% of this hydraulic force. Thank you. And we'll have some more lectures coming up.